Welcome everybody, my name's Ian and alongside of me I have Albert Kong. Also walking around will be Aman and Tristan. So we're tutorial on exploring open data in high energy physics. So Albert is a PhD student at the University of Adelaide. He's in the field of high energy particle physics, where Linux and the free open source software is used daily to analyse the wealth of data, open source data, within the field from contemporary experiments, mostly at the collider?
Yes.
In the CERN collider in Switzerland and Germany. No? France. Oh, it's just a border. Yeah. So, ladies and gentlemen, let's give a welcome to Albert and Aman, and please carry on.
Thank you for the introduction. Alright, let's head straight into it then. So, a very quick recap. Hopefully most of you would have seen Aman's talk earlier today already. So today we'll be looking at open data that's made available through CERN and Atlas. So CERN and Atlas. CERN is a large accelerator complex on this border of Switzerland and Germany. It's the largest particle collider that we have at the moment, with a circumference of 27 kilometers, about 100 meters underground. So the purpose of this accelerator complex is to both accelerate and collide protons, and these collisions are the data that we're interested in today. In particular, within the research of the field, we are trying to compare what we see in data to what we expect from theory. And this comparison is what gives us the results that are important to us. So a quick few notes on the CERN open data policy. There are 4 levels of public data that have been identified by this policy document they've drawn up, and it does make a bit of sense. So they break it up into these 4 levels. The first level are for published results that Aman spoke about briefly as well, where in addition to the academic journal article that we produce, we will also be including the data, the values that go alongside the plots and tables that we provide. And so these materials will be published under portals such as HepData. The second level are for simplified and portable data sets, and these ones are generally more tailored towards outreach and education type use. The third level are for research quality data sets, and these are the ones where even, I guess, would be close to what we would actually use in a real analysis. So this is the one where if you really wanted to try and make an impact yourself, you could try using one of these data sets and see what you can find. The fourth level is going to be very low level. So this corresponds to the raw data that we would be obtaining directly from the detectors. And this kind of thing you'd typically be seeing more for use in, say, some kind of experimental machine learning approach to better reconstructing the information that we receive. So for the purposes of today, we are more interested in the level 2 and 3 type data. So we'll see how far we get. We'll be starting off with something more like level 2, and we'll work our way up to 3 if we have time. So to begin with, we have a very simple setup to wet your, what's the expression here? Wet your teeth on? So if you'd like to follow this link that we have pasted up the top, it will take you to a little guided written tutorial that CERN has provided. And in particular, we would like to go to the histogram analyzer section, where you will find a set of interactive plots that we can start to play around with. And this gives you an idea of what it is that we might be doing. So, if you aren't familiar, histograms, similar to what we've shown on these figures here, have a number of these bars. So across the x-axis, we are showing the values for some kind of physical variable of interest. The y-axis is then how many particular events from this data set have that value on the x-axis. The, back. The different colors correspond to the different types of events that are in that particular bin. So for instance here, we have a number of different physical processes that we are observing within this piece of parameter space that we're looking at, as illustrated by these graphs. The green events then correspond to this particular process called TT bar. The orange ones correspond to ones from this WW process. What we're trying to do here is actually maximize the amount of this particular process involving this special Higgs boson relative to everything else that's going on. So if you have managed to get to the website that we've linked and go to that appropriate tab, you'll see, after a little bit of loading, the set of, I think it's 9 different plots. All of them are these kinds of histograms. And at the beginning, I think you'll see that you basically only see this particular Z process showing up. As you click around on them, you'll be able to set cuts where you require that events satisfy being within some particular range on that x-axis. And as you do this, all of the other histograms will update to reflect this extra selection that you've made. So try clicking around a bit and see how big of a significance you can achieve on this process. On the demonstration I've shown here, I managed to get a bit over 1. I think the best I saw was around 1.1. So see what you can do. Maybe you can get even better than that. We'll leave that for a couple minutes and see what people come up with. let's see if I can pilot this one and give an idea of what we were looking for. Uh-oh. Page not found. Oh, there we go. It's fixed itself. So we wanted to go to, I think it was this histogram analyzer tab, and too far. Here we go. There's a section here which looks like it's just a few titles at first with a scroll bar at the bottom. If we give it a while, it should hopefully load into that set of interactive plots that I mentioned. Perhaps with a bit more insight, I would have loaded this beforehand so we didn't have to wait now. So the goal that we're trying to achieve here is to increase the relative amount of this first process, this H to WW, relative to all the other processes. And at the beginning, you'll see that it's completely dominated by this one Z process. Everything else barely makes up a sliver in comparison. But by changing some of these selections that we have, by just dragging your mouse pointer across a few of these graphs, we'll set some requirements for the different events to have, and this can change the relative amount. One way to do this, you might not have figured it out at first, but if you actually click on one of these headings here, you'll set it to filter to only show the distribution for that type of process. So if we click on it for the Z, we don't really see much change because already at the beginning, everything is more or less just a Z type event. However, if you were to click on one of the other types, if I can click it, let's try that. Whoop. There we go. Oh, you have a mouse there. Okay, so here we can turn on filtering for the different event types. So if we wanted to filter for just the TT bar type, you'll now see what the distribution looks like for that compared to what it would normally with just the Zs. So what we would be more interested in doing then would be, okay, what about this particular signal process that we wanted? How does this differ compared to the Z? So we can then look at how some of these shapes for the different histograms change between when we filter for the H compared to the Z. So if you look at this particular one, called MET, we see for Z, it peaks very early on and then tails off rather quickly. Whereas if you look at H, the peak is actually somewhat shifted off from 0. So one idea we could try is if we were to place a selection where we want the events from this graph to, say, come in around, I don't know, 20, 30-ish, and go onwards. Because if we take off this filter again, most of the Z events are stuck near 0. So if we exclude the ones near 0 and take everything after that, we should get rid of a lot of Zs relative to this Higgs process that we wanted. So let's try doing that. To do this, we just drag a box, and let's just go all the way out for now. So really, we're just excluding the first couple bins. And already, we've seen a slight difference. This TT bar sliver is now somewhat larger, but we still can't really see H on the whole setup at all. So we've got a little bit more work to do. Let's take a look at some of the other ones. The next one, this PTLL, which is to do with the momentum of the two leptons. So this could be the electrons that we're more familiar with, or some of their more exotic counterparts that were found in that particular event. It looks like for this particular variable, the Higgs process has its peak somewhere around 90-ish, whereas for Z, that again is similar to the previous variable where it just peaks near 0. So just like before, if we were to place a selection band that, for now, let's just say goes all the way out, but excludes these first few bins where Z is most prominent, we should again see the amount of Z relative to everything else, hopefully, start to decrease even further. And we can repeat this process, going across each of the other fields and seeing how these shapes differ to figure out how we should be setting our selections. So this one up the top now looks like another nice candidate. For the Higgs, we have a nice big block all the way across and starts to drop off after 70 or so, compared to Z, where it's basically non-existent up until you get to around 90. So if we were to require it to be, say, less than 80 or so, that should help our signal quite a lot. And look at that. Now, after making that selection, Z is no longer the dominant process in our whole set, but actually TT bar is. And so this is the game that we'd be playing here, where we're going to be setting selections on some of our variables to try and reduce some of the backgrounds, until eventually that dominant background is actually no longer the leading process that we see in this whole set of data, but now something else takes over. But then we just repeat this until what is left is hopefully mostly the signal process that we're interested in. So we can just go ahead and repeat this process with some of the other variables. So now, since TT bar is the most annoying thing for us, this one here looks very suggestive because on this variable, there's only two values. On one of them, it's almost completely filled up by TT bar. So actually, I guess if we were to set a selection so that we get rid of this field, now that should drop our TT bar contribution almost down to 0 again. And so once more, this Z process takes over again. And so we just keep repeating this process until hopefully we slowly get this guy to creep up.
I think I'm having some trouble with the definitions. So when you talk about a process, the concept of using that.
Okay.
The physics of the process that generated data, using the physics that generated the data of which that sample is.
Okay, so the question is looking at the definition for a process as I'm using it here. So, okay, recalling that this data is about the proton-proton collisions that we're generating at the Large Hadron Collider. So during one of these collision events, a number of different things could happen. So the process we're talking about is what actually happened during this collision, what particles were produced. So in this one here, we're saying we produced this Higgs boson particle, which then did something else subsequently, which we don't really need to focus too much on the details here. These other processes are the other possible outcomes that would look like what we're doing here. So another thing that could have been produced after that collision is this 2Ws, or TT bar, or Z. So the idea is that we are interested in some subset of events with some characteristics. So it could be that, all right, this particular event had to have this number of leptons, for example, in the end. But in addition to the process of interest for us, which is this Higgs production, there could be other things that also satisfy that criteria. So this is something I actually get into on these slides in a moment. This is more of like a general play around first. Then we'll get you into a bit more of the theoretical grounding. Okay, so hopefully you were able to get a somewhat reasonable significance, somewhat similar to what we have here, 0.6. Maybe we can do better still. Well, if we look at the channel, you can see that most of the Higgs production is actually in this third channel, so we could also try setting a requirement on that. And that, again, boosts us up a fair bit. And now, actually, Z is out the window, and both of the other two are now taking over. So again, it's a game that we can just keep playing where, all right, we minimize one of these annoying background processes, something else takes over, now we try to deal with that one. And this is a very roughly accurate picture of what we're actually doing in some of these physics analyses. We have a particular process that we're interested in studying, but it's completely swamped by a whole bunch of other things that look very similar to it. So we try to separate them out as best as we can. Okay, let's head back to the slides then. That's not the slides. Here we are. So this is the problem that we're dealing with. It is very much a case of looking for a needle in a warehouse of haystacks, as I believe Tristan likes to say. So this is actually recapping what we were just discussing, where in physics analyses, we are interested often in isolating a particular process that we call a signal. The backgrounds would then be any other process that would come along looking similar to what we're trying to study. So on a single event by event basis, we may not actually be able to tell the difference between these two. But the idea is that on average, with a very large set of samples, we should be able to tell them apart. Now, an important thing to quantify how well we were able to isolate this signal from the background is this idea of significance. And, well, for the purposes of this tutorial, we'll go with this definition here, where it's going to be the number of signal events divided by square root of the number of background events. So remembering, signal is the one process that we're interested in studying, and background is just anything else now. Okay, so as a nice quick visual aside, another thing that we can do with this data is just try and cook up some visualizations of them. You've seen from Aman's talk, actually, some images that look somewhat similar to this, where we have some kind of detector geometry and a bunch of lines just exploding out from it. This is a representation of what that collision looks like just within the hardware itself. So we can open this one up if we like. I didn't make this one clickable, unfortunately. Nope. But okay, if you are interested, you can navigate to this website, and you would be able to play around with this thing interactively. It's a 3D model, more or less. You can rotate your camera around, move to different positions, have a look at what the detector roughly looks like, and explore a few different collision events in there, see if you can find something interesting. The other one, Atlantis, is more of a typical professional style event visualization that you might see in some more publications that we'll be producing. Whereas this kind of visualization is more like what you might be seeing in, I guess, more outreach type material. Okay, now on to the more technical side of things, where we're looking at how we can actually get our hands on the data itself rather than just using this very simple tool that we saw on the online website. So for this, I've prepared a little GitHub page with a Python notebook. So if you navigate to this link, you'll be able to open up the page yourself. So on the little README thing that displays, there'll be a clickable button that will then open it up in Google Colab. So we're using Colab to basically host and run the computation for this instead of you running it on your computer directly. So this makes setting up the required packages a lot more straightforward. Now, we have opened this one up already. Good. So this is what it should look like. And here, we'll be able to take you through the process of doing something similar to what we're doing on those interactive graphs, just ourselves with our own code. And hopefully this will give you a better idea of how you can actually do this on your own if you're so inclined. So the very first box here, this is where we now have to install the packages that we're using. And just like with many of the things here, we've done the hard work of figuring out what packages need to be installed for you. You just have to run it now. So to run this code block, you can, once you have selected your cursor in there somewhere, you can either use Shift-Enter to do it, or you can just click this little play button. And okay, let's try it. In my experience though, the very first time you try running this installation, it will do a bunch of things and give you a few warnings and errors at the end. So if that happens for you, and hopefully it will happen here so we can demonstrate, what you would then need to do is go up into runtime and use restart session and then run the same thing again. The good old tried and true, just turn it off and on again trick. Okay, there we go. We've failed successfully. So, as mentioned, when you do see an error and warning similar to what we see here, all you have to do is go runtime, restart session, confirm. And then once that's ready, it will say restarting up here. Now that it's all finished, let's just try running this block again. And now, it should hopefully work without any further issues. Okay, and there we go. We got the little tick of completion. So once you've managed to get that one done, we can now proceed with the actual Python side of things, which is what we're using in this environment here. So the first main thing that you'd usually be doing is just actually importing all of these different Python modules for use. And again, since we figured it out for you, all you have to do now is hit the play button to run these imports, and you'll see where we're up to an execution marked by that green arrow until we finished. So okay, nothing actually done yet aside from setting up which modules we're actually going to be using. In particular, the ones of interest to us are uproot. This is one of the various Python packages that we can use for reading the special root file format. So Aman mentioned root as this framework for managing large amounts of scientific data. Well, in order to unpackage it for use in Python, we are using uproot here. A few other useful ones to point out is pandas, which is a very common, I guess, library for managing large data sets. And this is what we'll be primarily using today. Okay, this next cell down, we have identified here a web address where you can actually get access to all of the data samples that we're working with today. So in fact, we can go ahead and copy that link and open it up in our browser, and you can actually see, there we go, you can see the different files that we're working with today. And each of these you can, in fact, just go off and do the old save link as from your browser if you wanted to download it directly rather than through code. Okay, so this is the list of files that we had under that directory, as we saw, and we're just setting up some of these prefixes and tree types settings for when we actually go ahead and use it later, and a little conversion scaling factor just to make sure we know what units we're working in. So okay, we can run this one pretty quickly. Now, this is where we give our first example of how we actually now get that data for use within a Python environment. So first, we set up a path for the full particular file that we're interested in. So we grab that path string from just above. We add to it a particular file from that list that we set up. So in this case, we're grabbing 0123, we're grabbing data D, appending it to the path, and then we're adding the suffix of .gamma.root. So this should hopefully match this full path here, plus this file name. Then, once we have this file name in place, we use the good old with context manager to then open via uproot that file with this tree type as a special argument to tell it what type of file it is that we're opening. And all we do then is we just save the result of it under this variable called tree, which we can then inspect and use as a regular Python variable. So in the lines following, we can, for instance, print out the number of entries that are available within this file. So basically, how many things have we got going on here? And you can also look at different properties associated with each of the events within that file. And of course, instead of just using this tree file directly, I mentioned before we have pandas for their nice, convenient data frames. So the last thing we do here is actually import that into pandas for use in their data frame format. So okay, let's run this and see what kind of output we get. Okay, so from this single file that we've opened up, we have, how many digits is this? 1, 2, 3, 4, 5, 6, so 3.6 million events from this one file that we've gotten. Maybe that's impressive. Don't know what your scales look like normally. The information stored under here, so these would be the different variables. So if we were to look at our previous one, so each of these would be one of the variables under here somewhere, or maybe something equivalent to it. Some of them, however, may only be for one value for this whole data set. So for instance, the I think the scale factors probably are going to be the same for all of the events here. We'll see. Some of them will be for one value per event. So then something like the, where's it good? Okay. Something like event would have some number of photons in it, but then each of the photons within that event will have their own individual properties. So looking at these guys here, for example, every single photon within the event would have their own set of PT, eta, and phi. So there is a little bit of nuance to what each of these variables would look like. So to get a better idea for that, we can actually now start to investigate these things individually. And to do that, we have a very simple syntax. So we saved the data under this variable df for data frame. And all you have to do to inspect what a particular variable looks like is just use this square bracket indexing and give it that variable name. And that, if we just run it as is, will just print out an array slice that looks something like this. So it will give you a preview of it, and obviously it truncates it because you don't want to show that many million events just in one line. But okay, it does tell you that it has the whole number of things here, and if you wanted to go even further, let's go slightly off the rails and add another code block. What we can do is, in addition to indexing by the I can't type and look sideways, jet n. So in addition to indexing by the variable name, we can now also give it a particular variable index. So say if we wanted number 3 here, we could just give it 3 and print, and we should then hopefully see the value 5 pop out. Okay, there we go. Not too controversial, I hope. But you can also get a somewhat fancier if you wanted to. So this one does support the usual slicing operations that you'll be familiar with. So say if you wanted the entries between 3 and 5, we can also do, oops, not like that. That should be a colon. So there we go. Now we get 3 and 4, but not 5 inclusive. So okay, this works as you might expect with most of the usual Python data types. So maybe I'm already preaching to an audience that knows all of this stuff. We'll see. So once you've had a little time to fiddle around with this yourself, maybe I should give you a bit of time. The next thing we'll do is then look at how we're going to make use of this information to do something a bit more like what you'd expect in a physics analysis. Any questions so far?
No, that was me going on and doing something else. But how I got to
Okay, so after we've had a little bit of playing around with what's included in this big table of values, now let's see what we can actually do with this in terms of the physics side. So the first thing we would like to do is see if we can make a histogram somewhat similar to what we saw on these other sites here that we were playing with previously. So to help out with this, I had defined a rather long function that helps with doing this, but okay, we'll step through it. There's a lot of stuff here that's mostly boilerplate to set up the aesthetics of it. That's not too important to us. The important ones would be more at the beginning, where we're setting up the binning for that histogram. So remember the histogram, if we just go back to the image for it to give you an idea, we're showing a particular variable along the x-axis, and we're splitting it up into little bins of some certain width going all the way across. So for this one here, it looks like we're using, 10 units across for each bin. So that is something that we can set up here on our own. So the first thing we want to do is define the minimum and maximum values of the range that we want to show. Here we have some setup that lets us have a default value if we don't provide one explicitly. That would be inferred by the maximum and minimum values for the data that we input, so a somewhat smart system. Then we calculate what the bin edges and centers would be using some handy functions from NumPy, a common computational framework for use here. Then, after we have these acquired, we feed them into the histogram function to create what the groupings would be for us. So that would just give us the counts of events in each of the bins as one of the outputs, and the other output I actually don't remember what it is. We just discard it really. And okay, we can also generate error bars for the points as well, just by looking at the square root of that count. It's relatively simplistic. Then the rest of the code, as marked out here, is just really for setting up the plotting side of things. So as I mentioned, it's not that big of an interesting point for us, so I'll just skip over for it. A lot of it is just setting up things like your different tick markings, your axis labels, X and Y limits, that kind of thing. Although hidden away at the bottom is another little convenience function I provided, which lets you convert the column that you'd extract from the full data frame to something that we can pass inside this plotting function. So, okay, how can we make use of these functions? Don't forget to actually run this, guys, so that the definitions are available within your environment. And then we can come down to this block here. So what are we doing? To actually make a histogram, all we have to do is pass it into that makeHist function that we had just defined. Okay, so this commented out example I think was for use with a older data set, which I think we may not have that variable anymore. So, okay, this uncommented version here is the one that should work if we were to run it. So what are we doing? We're making a histogram of this particular variable, jet, and the number of jets within an event. Bin size is 1 because a number, so we're expecting some kind of integer valued variable coming out here, and we're just setting a range between 0 and 10. So again, these limits and binnings can and probably will change between variables, so a little bit of experimenting may be needed to get an appropriate scale for each of them. But okay, let's just try this one and see what happens. And here we go. We get a histogram coming out. It doesn't look exactly identical, but is functionally the same as what we were looking at before. So we have bins going across. In this case, our bins are covering just a count of 1. So this first one here, I guess, would be coming 0 to 1 not inclusive, something like that. And we're just going across this way. So based off of this, we'd see that actually most of our events would have up to 2 jets, and then after that, it falls off very quickly. The other big difference that we'd notice is that here, we only have one process, really, just umbrella term of data, whereas previously, we had looked at these kinds of histograms where we're now actually showing contributions from different processes. So again, this is coming back to the difference between having just the data versus also having the simulation to accompany it. Because when we have data, we don't actually know what's going on in reality, whereas when we've gone and simulated it ourselves, we know what everything was under the hood. And so that gives us a little bit of, I guess, back and forth between the two types, because with the simulation, we now know what is doing what, so we have an idea of how to tune our selections. But then when it comes to data, we don't know what things are, so now we have to rely on our simulations to inform how we should treat the data.
You can have to check your code so you know you're not going to generate junk.
Yeah. So, yeah, I guess it is trying to show the point that simulation is very important for us here. Okay. So this is a very simple thing that we can do, and using this kind of code, you can go ahead and make similar plots for the other variables as well if you wanted to. And I pointed out before that some of them would have multiple values per event, so maybe I could actually have shown this up here as well. So here, when we just plot this value of jet and, well, just print out this column, you'll see that we have the event counts going up, and each one has a single associated value. Whereas if we were to change this to, what's one that would be here, say PT. So this would be a value, and we should see that each, yeah, here we go. So associated with event 0, we actually have one value here. But then if we go to event 2, which presumably had a value of 2 jets when we looked at that printout, we have, well, actually not just 2, we have 3 distinct values associated with it, one for each of the jets that were present in that event. So trying to then print out a histogram for this, we would need to account for this extra array that is associated with each event rather than just being a scalar value for each. So that's what this whole flattened business is for. When we have these array-valued variables, you would have to flatten it out before we can histogram it. So I left a little box here where you can insert some more histogramming of your own if you want to play around with some. Probably shouldn't give too long for that one though, since there's some more interesting stuff to come. So, okay, if we get extra time at the end, maybe we'll come back to it and let you play around with it then. Another thing to note then is this flattening operation does consume a fair bit more time, as you're seeing, compared to when we can just plot the thing directly, since now we have to convert this somewhat vectorized format here into one that's completely linear. So then each of these ones which contain multiple things has to get expanded out into 3 separate entries and so forth. But okay, eventually it will run and then we'll get another histogram of our own here. So while this guy's crunching, let's continue on with the next step in our process. So, okay, earlier on, Aman was showing you a final result looking plot that you might see in a publication, which we used to show the evidence for some particular process. So this is the kind of thing that we'd like to try and create ourselves. So again, just like the previous, I've defined a handy little function that does most of the work for us. All we got to do is pass it in some variables. So what do we need for this one? Just like before, we tell it some information about the binning that we want, because again, it's a histogram that we're creating. This fraction here is saying what fraction of the whole data set that we want to include. For us, we just use 1 to say everything. If you want, you can use, say, 0.5 to say only include half of it too. That way it will run a bit faster for you. The other important thing here is actually passing in the data set that we want to process. So what do we do here? So we have a similar binning setup to what we had previously. And now, this is the thing that's more specific to this final result plot that we want. So again, this is about fitting what we expect the process to do compared to what we actually see. So there's 2 things going on. First, this here is trying to make a model of what we are seeing. So we have a baseline polynomial, and then on top of that, there's a Gaussian that's sitting somewhere. And the idea is that we are going to fit these two models as a somewhat like a least squares fit type approach to whatever data points that we actually get in the end, and see what comes out. The expectation of, let me try a different wording. So we have the two things. We have what we would expect the data to do if there was no signal, and then what we actually see. So then the other part to this would be, well, what is this background doing? And okay, I think this one's not laid out too well. But okay, in the end, it turns out that this polynomial thing is our model for what these background processes are doing. And then the inclusion of the signal ends up being this Gaussian part that lies on top of it somewhere. So later on, we assemble the model as the addition of these two pieces, and then we're fitting all the parameters for these models together here. So, okay, there's a lot of these stats packages at work here to do all of this for us, so that we don't actually have to do a lot of the heavy lifting ourselves to get this done. But okay, we're extracting all the parameters from the fit here. Then we recreate the function that we're actually fitting to, which is this fourth order polynomial. So some constant plus a linear term plus a squared term, cubed term, fourth term. And then the last part is we then can look at the difference between what we're seeing and then what we were expecting to see from that background fit. And this is the one that lets us see a little bit more easily what signal there is, because oftentimes, despite our best efforts at reducing the background contamination, there's still going to be significantly more background compared to signal. So this one lets us see that signal piece a little bit more clearly. Okay, and then again, there's a lot of stuff about setting up the actual appearance of the plot, so we won't worry too much about that part. Okay, and then again, hidden at the bottom is another little utility function for calculating an important quantity to us, which in this case would be, we have two different photons in each of the events that we're looking at, and we're going to be reconstructing the mass of the particle that they would have come from, assuming that they did in fact come from a single particle. Okay, so as before, remember to actually run this guy so that the definitions are available to you. And now, in this next section, we will be accumulating together all of the different data files that we saw earlier. So remember, when we looked at the website directly, we saw there were 4 different files, and we were just playing around with the values from one of them before. But we'd like to make use of all of it if we can. So that's what this next piece here is doing. We're going to be grabbing each of the files in our list that we had before, and then we'll process each one by opening it up, printing out the events for us somewhere. We'll calculate that mass value using the function we had at the end there, this calcmass function, and then we'll save it to that data frame under a new column. We just call it mass. Then we append all of that together into one big list, and then at the end of it all, we can convert that back to a data frame for, again, convenient access. So okay, we can run this, and it might take a little bit, so probably should have gotten that started while I was explaining it. But okay, we'll give you a little printout as it gets to each of the samples, and we should see 4 of these then. bug reports. Uh-oh. Go ahead.
Min equals 0 in the plot histogram function doesn't do anything because the if treats 0 the same as none.
Ah, that's a tricky one. Okay. Yeah, again, that was a relatively quickly cobbled together thing, so maybe not too surprising there is in fact a bug in it. But alright, noted. We could try and fix that one then. I think we can just do a comparison to none. That sounds like it would work. Where did I do that? I think that was in the previous one actually. Here, right? Yeah. Equals x min if x, pressing all the wrong keys. Min is not none. Else, I think that might work. See if the reporter's happy with this one. Alright, there you go. There's your dose of live coding for the day. And of course we've got to remember to run this so you get the updated definition. Alright. Well, the good news is the stuff later on doesn't actually rely on that, so we should be safe. Okay, where were we? We were running the thing that amalgamates all of the different data files together, and alright, it looks like it's done now. Good, so we can go ahead and actually just run our result plotting routine as is, just after accumulating everything together, and see what happens. So the thing is, this may not actually look too good, because as mentioned before, you typically have a much higher amount of these background events compared to the signal events that we're interested in. And okay, that is very much what we're seeing here. So we had a background model, which was that fourth-order polynomial, and we said that maybe somewhere there's a, what's it called again, Gaussian that's sitting on top of it, which would look like a little bit of a bump. But unfortunately, nothing was picked out in this particular setup. You don't see any polynomial, sorry, you don't see any Gaussian bump shown in that fit. So this one's not so good. Intentionally so, perhaps, for the purposes of this demonstration. So what we do then is we should be applying some of these selections, or cuts as we call them. So this is the equivalent of what we were doing here, where we were able to just drag out to set some bounds for these variables. We're doing something equivalent now, just in code to, well, do this in a more automated fashion. Okay, so what do? We would like to have some requirements on the data. So to do this, in this case, we set up some functions that we can use to just group this all together. So here we would say, okay, we are given a variable, this particular photon is type thing, and what we want to do is we just wanted to check that this value is true for both of the photons in an event, and similarly for the other one. So for this one, we're checking against the transverse momentum, that's what PT is, and we're just checking that for the 0th one, it has a value greater than 40 GeV, and for the first one, it has a value greater than 30. And again, we have checks for other variables as well. So these follow along similarly to the others. And okay, someone somewhere has done the work for you to figure out that these are some useful selections to make. So this part is equivalent to what we were doing before, where you were just playing around with the different selections you could do and see what ones would be useful to minimize your backgrounds relative to your signal. So this is the playing around bit, or the research part, perhaps you might say. But someone has already done that work for you and say, okay, this here is a list of good selections to make. So okay, let's go ahead, we'll run this to get these definitions, and then we can apply them and see how that helps us out with picking out the signal that we are interested in. Okay, So now that we have these selections in hand, we will want to apply them. So this is the setup that I came up with for doing it. So we start by just setting our selected data to be equal to the whole thing that we had conglomerated together to begin with. And we can print out the number of events that we start out with. Then we would do a somewhat repeated process of taking this and setting it equal to first all data. Well, I guess this could have been itself again here, where we index by this function. So the function is going to be returning a Boolean array. So saying for each event, does it satisfy this condition that we have? And by indexing with a Boolean array, we're just picking out the things which are true. And okay, there's some junk going on here to make sure it all plays nicely with the shape that it's wanting it to be. So in the end, we're just saying all the events that satisfy this condition that we laid out before, we will keep. Everything else we are discarding. And we just do this process iteratively. So at the next level, we grab what remains from the previous level, apply another selection to it to get another Boolean array, reduce the data, and see how this keeps dropping over time. So okay, let's have a look at what happens here. So to begin with, we've got this number of events. So you might notice that this is a smaller number than what we saw originally. So that is because originally I think it had included each of the individual things. So I mentioned before that there are some vector valued quantities in there. I think it was counting each of those vectors as fully expanded out. So here this is condensed down to just the events that we have. So okay, after doing these cuts, we can see that it keeps dropping in the number that we retain after each level, which is to be expected. But we still have a relatively large number at the end. So this is 79,000, almost call it 80,000. Okay, and what's left to do? Let's just create that result plot again on this reduced selected data set and see how that helps out with our final result. And okay, looking at the initial thing, it's hard to see the bump here, but okay, that's why we have this subtraction thing here where we can actually see it in a little bit more detail. Okay, so with that, it gives you a taste for what a more typical analysis process might look like. So we start out with a few data sets that you might have access to, either because you're part of the collaboration that recorded it, or maybe it's because you now have access to the open data that we've published for you. Then you assemble together what you want and you cook up a model for what you expect to see. So again, this is something that we didn't really look at in this example. So here, to come up with what we expected to see, this background, we just said it's a fourth-order polynomial. Why is that? Well, for this, it was really just for demonstration purposes. But in reality, you would have to do some more of this complex modeling that is very computationally expensive to do. And using that, you would be able to get some idea of the different contributions, similar to what we were showing in this interactive tool here. With these ideas in mind, you can then set up some selections, so similar to what we were doing here, that would then let us maximize the amount of our process of interest relative to the other background processes that are present within whatever events that you're interested in. Once you've done that, you can apply those selections to your data, then create your final plot, and hopefully you'll have picked out the existence of some new particle that no one has seen before. And that is physics in action.
Thank you very much, Albert. That's been very interesting, and the participants have learned a lot and played with the software, which is
Open source.
what we're looking for. It's open source. So it's open data, open
everything.
source, open. It's fabulous. I love it. So thank you very much for presenting that rather technical, but for those that want that, very interesting presentation. And we'd like to say thank you for giving your time to the Everything Open conference. And this is a token of our appreciation for you. This is being created by Stuart, one of our core volunteers, and I think it's pretty cool. So it shows the city and the cathedrals and the streetscape.
Well, thank you very much.
That's rather
It's been
cool.
my pleasure.
So thank you very much. If you'd like to show your appreciation.